Today we are walking through the paper titled Harnesses that improve themselves.
What is the central idea here?
The paper is about LM-based agents that improve the harness around themselves. A harness is the non-parametric scaffolding that decides how the model receives tasks, uses tools, checks what, recovers from failures, and produces a final answer.
So the paper is not training a new model. It is changing the wrapper that controls how the model works.
Exactly. The authors argue that the same base model can perform very differently under different harnesses, but those harnesses are usually hand-engineered, which becomes hard to scale when models are diverse and keep changing.
What does self-harness change compared with that manual design loop?
Self-harness lets the agent use its own execution evidence to propose and test bounded changes to its harness. It does not ask a stronger outside agent to redesign the system, and it does not change the base model parameters.
In this comparison, the key shift is who performs the improvement, right?
Right. The human engineering path puts people in charge. The meta harness path uses a stronger external agent. Self-harness moves the improvement step into the target agent's own loop, while keeping the evaluator fixed so accepted changes have to be earned by performance. The loop has 3 stages. First, weakness mining groups failed execution traces by shared failure signatures. Second, harness proposal generates several small candidate edits. Third, proposal validation keeps an edit only if regression tests show improvement without a trade-off on the other split.
How do they avoid treating one strange failed task as if it proves a general problem?
They do not use failures as isolated anecdotes. Each failed run is represented by a record containing the task, the trace, the produced answer, and the pass or fail outcome. Then failures are clustered only when they agree on the verifier level cause, the behavior's causal status, and the reusable agent mechanism exposed by the trace.
What is the failed record set used for after that?
The failed record set focuses the proposer on cases where the current harness broke down. In notation, it is the subset of round records whose outcome is fail that lets the system mine recurring failure mechanisms instead of rewriting the harness from vague impressions. Once a cluster is selected, candidate edits are generated in parallel. The paper emphasizes the constraints. Branches should be diverse enough to test different hypotheses, but each edit should be minimal enough to preserve unrelated harness behavior.
What makes validation stricter than just accepting a plausible edit?
A candidate has to improve at least one evaluation split while not degrading the other, so the loop can promote changes that help on held-in evidence, held-out regression tests, or both, but it rejects changes that simply move the error around.
What benchmark do they use to test whether this actually helps?
The experiments use terminal bench 2.0, where agents solve tasks through terminal interaction in containerized environments. They start from the same minimal deep agent-based harness and run self-harness for 3 different base models: Minimax M 2.5, Q1 3.5 35 BA3B, and GLM5. The headline result is that held-out pass rates rise for all 3 models. Minimax M 2.5 goes from 40.5% to 61.9%. Q1 3.5 goes from 23.8% to 38.1%, and GLM5 goes from 40.9% to 57.1%.
Those are all improvements, but are they the same kind of improvement for every model?
No. The qualitative evidence says the accepted edits are model-specific. For Minimax M 2.5, retained edits address missing required artifacts, schema invalid tool content, and stalled tool use loops. That produces a harness that creates required outputs earlier, handles structured tool content more carefully, and redirects execution after long tool interaction.
So for Minimax, the harness mostly pushes the agent to leave the right artifacts behind.
That is the main pattern reported for that run. The pass rate improves from 42.2% to 53.9% in the evolution analysis, and the retained edits target concrete execution failures rather than adding one generic instruction for every backend. The Q1 3.5 run starts at 20.3% pass rate and reaches 36.7% after merging edits around artifact checking, missing artifact recovery, retry discipline, and error-triggered middleware. The change is about recovering from file editing or tool failures while still leaving verifier-required artifacts in place.
And what changes for GLM5?
For GLM5, the harness improves from 46.1% to 57.0%. The retained edits target late artifacts, external computation, session scope tools, and implementation-oriented exploration. So environment changes persist across shell commands and the agent moves from prolonged exploration toward implementation and testing.
What does the paper claim from these different retained edits?
The key claim is that self-harness is not merely appending generic advice. It turns model-specific weaknesses into concrete harness changes, then keeps only changes that survive the regression gate under the same model. evaluator, and benchmark protocol.
What are the limits of this result?
The paper is careful about that. This is bounded harness editing under fixed benchmarks, not open-ended self-improvement. Accepted edits may reflect benchmark-specific failure patterns, and the protocol depends on verifier quality and trace quality. Higher stakes harness changes would need stronger acceptance gates than pass rate non-regression alone.
Then what is the final takeaway?
The takeaway is that harness improvement can be treated as an empirical state transition. A useful edit should say what behavior it aims to change, what harness surface it modifies, what evidence motivates it, and what evaluation result justifies promotion.
So the agent is not just being shaped by a harness. It can also help improve the harness when the loop is constrained and tested.
Exactly. That wraps up this paper walkthrough.